electron configuration of manganese. Remember, just read across your periodic table, 1s2, 2s2, 2p6 takes you across second row, 3s2, 3p6 takes you across the third row, and then we get to the one where manganese is, and you have to remember that it's 4s2, but it's 3d10, not 4d, sorry, 3d5 in this case, not 4d. So that's the highest energy subshell in manganese, so the answer is that there are no 4d electrons, and so the answer is A. Question 2 is a cunning way of checking whether you know about both the trend across a period and the trend down a group. So if we think about, because these elements are in period 2 and in period 3, so let's think about period 2 first of all. And remember the trend goes like this, that we get lithium, beryllium, and then the first of the blips in the trend, where we're switching from 2s to 2p electrons, and that makes it slightly easier to ionize. So we get boron and then carbon and nitrogen, and then we get the other dip, but we don't really need all of this at this point. That's just to remind you really, but we only needed to think about that bit. So that tells you that boron is lower than beryllium, and so that straight away rules out beryllium as a contender. But then you have to think about the trend down the group, and remember the trend down the group is that ionization energies decrease. So if this is, as we know, ionization energy going up here, we're going to have sodium and magnesium and aluminium, same trend as before, and then silicon and phosphorus. And so you can see that that one is the lowest, because it's lower than magnesium in period 3, and both of them are lower than the ones in period 2. So aluminium has the lowest ionization energy, so that's the answer for that one. In this question you just have to remember that these numbers are the mass numbers, and that those numbers are therefore equal to protons plus neutrons, the number of particles in the nucleus in each case. So for uranium-235 you look up the atomic number on your periodic table and find that it's 92. So 235 minus 92 is 143 neutrons for the uranium. Fluorine, again you look up the atomic number is 9, so you get 19 minus 9 is equal to 10 neutrons times 6, because there are 6 fluorines there, and so the total number is 143 plus 60, which is 203 neutrons, and therefore the answer is D. The thing with oxidation states is to remember that they add up to the charge on the ion. So we've got 4 oxygens, and oxygen in compounds is -2, so we've got 4 lots of -2, takes us to -8, so we've got to get from -8 to -2, which means we need +6, and we've got 2 carbons there, so that's 2 lots of +3 is the average oxidation state for the carbons. So we've got +6 -8 gives us -2, which agrees with the overall charge. So +3 is the answer, which makes it B. Question 5. Magnesium in group 2, remember, has 2 delocalized electrons per atom, because both the outer shell electrons will be delocalized, whereas sodium in group 1 has only 1 outer shell electron, so 1 delocalized electron per atom. And that means that magnesium is going to be a better conductor of electricity, just because it's got more delocalized electrons to do the conducting. So A is true. And it's also going to have stronger metallic bonding, because it will have 2 plus ions rather than 1 plus ions, and therefore a stronger attraction with the delocalized electrons, as well as more of them. And therefore, for both those reasons, you would expect stronger metallic bonding for magnesium, and therefore a higher melting point. So B also is true. C, you have to remember this thing about solubility of group 2 hydroxides, that they decrease as you go down the group. So magnesium hydroxide has very low solubility, and as you go down towards barium hydroxide it increases. You don't have to know why that is, you don't have to be able to explain it, but you do just have to remember that fact. And so you know that magnesium has a very low solubility hydroxide, Sodium hydroxide, you might think, well, I don't know, but of course you do, because you've used sodium hydroxide solution lots of times in practicals. You know that it's a very soluble substance, hence you can use it as an aqueous reagent. So the answer is magnesium hydroxide is less soluble than sodium hydroxide, so C is false. So C is the answer for this one. Just to confirm, D, you almost don't need to work this out because you know the answer is C, but it's quite an interesting one, so it's worth just going through this. So we've got sodium is 1s2, 2s2, 2p6, 3s1, whereas magnesium is almost the same but just with the extra electron. So 2s2, 2p6, 3s2, and it's asking us about second ionization energies. So for sodium, the first one will take that one away. So the second ionization energy will be removing an electron from 2p. For magnesium, on the other hand, it's got two outer s electrons, so the second ionization energy will be from 3s. And that's going to make a huge difference because this 2p subshell is closer into the nucleus, much less shielded from it. That's going to outweigh the very slightly higher charge of magnesium and make these electrons much more strongly attracted to the nucleus. So the second ionization energy of sodium you expect to be considerably higher, and therefore D is true. So that confirms that C was the right one. Obviously that took a bit of thinking through, so the smart way to do that question was to realise that C was the answer and then almost not to bother with that one. So make sure you don't spend too long on any of these individual 1-mark questions. Okay, question 6. You have to remember that if you have an alkane, the general formula is CnH2n plus 2. So if we've got 27 carbons, which is what it tells us cholesterol has, if it were an alkane, it would have 2 27s of 54 plus 2 is 56. But it tells us, first of all, that it's got one alcohol group, an OH group. So if you compare OH with H, you can see the only difference is that it's got an extra oxygen. So that's the first correction we can make, that it's got an extra oxygen, but that doesn't cost us any hydrogens because you've just inserted the extra oxygen between the C and the H. But it also tells us that it has 4 rings, and you have to remember that you lose 2 hydrogens for each ring, which means that you lose 8 hydrogens because you've got 4 rings, and you also lose 2 hydrogens for each alkene group, for each C double bond C. So that means another 2 hydrogens are lost because it tells us there's one alkene group, so 10 hydrogens are lost altogether in making that into cholesterol. So we've got to take 10 away from that, which means that we get C27H46O is the correct formula, and therefore the answer is B. Question 7 is all about Le Chatelier's principle. It's saying what can we do to make this equilibrium shift over in the forward direction, over to the right, so that we make more HCN. So the first thing it suggests is decreasing the temperature. Now remember, Le Chatelier says that whatever change you make, in this case decreasing the temperature, it will do the opposite. It will shift in the direction that tries to take the temperature back up again. And so if we decrease the temperature, it will go in the exothermic direction, the direction that gives out heat to try and oppose the change. Now when it quotes delta H for a reversible reaction, you need to remember that that means that's the sign for the forward reaction, and obviously the sign will be the opposite for the reverse reaction. And so it's negative in the forward direction, which means exothermic in the forward direction. So that's the direction it will shift, and that does make HCN. So straight away you know that A is the answer. So again, if you're in any kind of a rush, you just write down the answer at that point and move on, but we can just check that the others indeed are not correct. So increasing the pressure, well remember, if you increase the pressure it tries to decrease it again, and it does that by shifting in the direction where there are fewer moles of gas. So if we have a look, we've got 1, 2, 3.5 moles on the left, but 4 moles on the right. So more moles on the right, that means if we increase the pressure, it will shift to the left in the backward direction, so we'll get less HCN, so that's no good. Using a catalyst, key thing to remember about catalysts is that they don't affect anything to do with equilibrium. They don't affect delta H, they don't affect the position of equilibrium, because they increase the rate of the forward direction, but they also increase the rate of the back direction by the same factor, and so you just end up going around in circles quicker, but you don't shift the position of equilibrium. So definitely not C. And if we inject additional steam, well, steam is here on the same side of the equation as HCN, so if we put more steam in, it will shift in the direction that uses up steam, that tries to oppose the increase in steam concentration, so that means it will shift in the backward direction, and of course that will not just use up some of the extra steam, it will also use up HCN, so the HCN amount will decrease. So that confirms B, C and D are all no good for increasing the HCN amount, and therefore A was indeed the answer. Okay, so for question 8 we have to set up a Hess's law cycle so that we can solve for the missing numbers. So it tells us that the standard enthalpy change of formation of xenon hexafluoride is minus 297 kilojoules per mole. Formation, remember, means formation from the elements in their normal state. Xenon is a noble gas, so it's just Xe. Remember, noble gases just exist as atoms. And fluorine normally exists as F2. So to make XeF6, which is what we're trying to make, we're going to need 3 F2s. Now bond enthalpies, so that's minus 297. Now bond enthalpies are the enthalpy changes when you break 1 mole of bonds. So what this is telling us is that if we put atoms of the elements down here, in other words Xe plus 6F atoms, plus 155 is the change when you break 1 mole of F2 molecules up into atoms, so breaking 1 mole of FF bonds, but we need to break 3 of them, so this will be plus 155 times 3 to go in that direction, which is plus 465 going in that direction. And we want to know the XeF6 bond enthalpy. Well, if you go from there to there, you're breaking not just 1 XeF bond, but 6 XeF bonds. So this is 6X, where X is equal to the XeF bond enthalpy. Okay, so we can just quickly scribble down a cycle like that, and then we've basically got to solve for X. So what we can do is just write a little equation which says that plus 465, so going from there to there, and then we need to go carry on in that direction, because remember our indirect pathway to match the one at the top is going to go like that. So plus 465 minus 6x is equal to minus 297. So therefore 6x, if we just rearrange that, is equal to plus 465 plus 297. And so if we just do that sum and divide by 6, we get x is equal to plus 465 plus 297 divided by 6, which is plus 127 kilojoules per mole, which is answer A. Okay, so it seems like that's a lot of work for 1 mark, but of course you don't have to set it all out clearly like that. So if you've practiced a lot of these, you can do that in a very rough kind of way and do that manageably within a minute. But if you're finding it's taking a long time, skip it, move on, come back to it if you have time. You know, these multiple choice questions vary hugely in how challenging they are, how much time they're likely to take to work out. So what you can't afford to do is throw away a lot of time on a 1 mark question. So just, if for example you found that challenging, the thing to do after 30 seconds, 45 seconds would be to think, yeah, this is taking me too long, I'm not getting anywhere with it, mark it, come back to it if you can. But that was the answer, which is A. Okay, so question 9, in contrast to question 8, is one that's actually really quick if you spot the issue. So it's asking us about boiling points, so remember we have to work out what kind of forces have to be broken and consider their strength. And these three substances you should immediately realise are simple molecular. It doesn't matter that you may be unfamiliar with F2O or even with CH3F. You might think, well, I've never come across that compound, so how am I supposed to know what it is? But these are both non-metals, these are all non-metals, so you know they're going to be covalent compounds, and you can always assume that they're simple molecular as opposed to giant molecular, unless it either tells you otherwise or gives you information that could lead you to conclude otherwise, like telling you that the melting point was very high. But normally if it's a covalent compound, you should assume it's simple molecular, and that means that you only have to break intermolecular forces to turn it into a gas. So you expect these to have relatively low boiling points because you don't need to put much energy in to break those intermolecular forces. This one, on the other hand, we have a metal and a non-metal, so this is going to be a giant ionic structure. And of course that means that you have to break the very strong ionic bonds to vaporize it, so this is going to have an enormously high melting point. So you could see that instantly if you looked down the list. So the important thing was not to get bogged down in thinking about the details of what sort of intermolecular forces were formed here. Look down the whole list, see that one and think, oh yeah, that one stands out from the crowd because it's the only ionic one. It's going to have a much higher melting point than anything simple molecular, and so that's the answer. Question 10 wants us to consider ammonia, which is that, and it asks us which of the statements is true. So the first one says ammonia is less volatile than water. Remember, volatile means easy to turn into a gas. So if that were true, it would be harder to turn ammonia into a gas than it is water, and that's obviously not the case because ammonia is a gas at room temperature. Water is not, it's still a liquid, so it's harder to vaporize water. So A is wrong. Saturated solution, well remember ammonia is a base, so remember it does this reaction with water where it takes H plus ions away from the water to give you NH4+, and that leaves OH minus ions behind, and therefore ammonia solution is alkaline, so its pH will be above 7, and therefore that's clearly also not true. The HNH bonding, we have to think about the shape. So remember ammonia has 3 bonded pairs, 3 which are the 3 bonds to the hydrogens, and that leaves it with 1 lone pair in the outer shell. You could scribble down a quick dot and cross diagram if you needed to, but hopefully this is one of those examples that you actually just know straight off is because it is that shape, because it's the classic pyramidal molecule. And remember that in a pyramidal molecule the angle is indeed 107 because it's 109.5 in a perfect tetrahedron. But because lone pairs repel more than bonded pairs, it closes down the bond angle a little bit, and 2.5 degrees per lone pair takes it down to 107 degrees for a pyramidal molecule. So C is the correct one. We could therefore move on and ignore D, but just to check, can you make ammonia by reacting an ammonium salt with nitric acid? Well, no is the answer to that one. That one is false. The way you get ammonia from an ammonium salt, remember, is by reacting with aqueous sodium hydroxide, with an alkali, not with an acid, because then you get this reaction where the NH4+ ion reacts with the OH- ion to form ammonia and water. And when you warm it up, the ammonia comes off as a gas. So that was would have been the correct answer, but it's wrong with acid. So C was the only true one, and therefore that was the answer. Question 11, we have to do a quick calculation. So we've got CrCl3 with an unknown number X of waters, and we're told that it's 40.5% H2O. So a quick way to do it is think, well, if you had 100 grams of it, that would mean that that was made up of 40.5 grams of water, and 100 minus 40.5 is 59.5 grams of CrCl3. And of course we can just turn those two masses into moles. So 40.5 divided by 18 will give us the moles of water, which is 2.25 moles. And for this one we've got 59.5. If we add up the MR of that, we've got 52 for the chromium. 3 lots of 35.5 adds up to 158.5. And if we do that division, that comes to 0.3754 moles. And then we just need to find the ratio of those two numbers, because remember that's what X is. It's saying how many waters are there for each chromium chloride. So it's moles of water divided by moles of CrCl3. So that's equal to X is the moles of water divided by moles of CrCl3, which is 2.25 divided by 0.3754, which is 5.99, and therefore is effectively 6 is the value of X, and therefore it's CrCl3 6H2O, so C was the correct answer. Right, so for question 12 you have to remember that density is equal to mass over volume. That's an important definition to remember, and in this case, because it gives us the density in grams per dm cubed, that's going to be the mass in grams divided by the volume in dm cubed will give you density in grams per dm cubed, which is what we've got. So if we just rearrange that, we can get therefore that mass is equal to volume times density. And the reason that's useful is that for 1 mole the mass is equal to 24 dm cubed, because we know that that's the case for 1 mole of any gas at room temperature and pressure, times the density, which it tells us is 0.708 grams per dm cubed. And if we multiply those together, that comes to 16.99, which is therefore 17.0 to 3 significant figures, 17.0 grams per mole. And of course the mass of 1 mole is the same as the MR, so that means that the MR is 17.0. Okay, so that's a very standard trick that you need to be able to do with gas density. So make sure you can see that that makes sense. It begins with learning the definition for the density, making sure you can just rearrange it like that, and the key thing to remember is that for 1 mole you know what the volume is. At room temperature and pressure is 24, or indeed at other conditions you could work it out with the ideal gas equation. And therefore you can deduce the mass of 1 mole, which is the MR. So you then look at those candidates and say, well, which of those has an MR of 17? Not chlorine, because atomic mass is 35.5. Not hydrogen chloride, because the atomic, the molecular mass of chlorine is 71. HCl 36.5, but ammonia is NH3, so 14 plus 3 is 17, so C fits. Carbon monoxide, you have 12 plus 16 is 28, so that doesn't fit. So it had to be ammonia, and therefore that was C. Question 13 is taking you through the standard sequence of tests for negative ions, but with one extra little observation in there which was important as well. So first you do the test with acid, and you find that with aqueous sulfuric acid you get no effervescence. And remember, if it doesn't effervesce with an acid, that means it's not a carbonate. Okay, so we can immediately rule out option C, because that was a carbonate, so it can't be that one. But it did give a white precipitate, so you have to think, well, why might you get a white precipitate with sulfuric acid? And the thing to do is to think not about the H plus ions, but think about the sulfate ions, because we know that sulfate ions precipitate out to form a white precipitate with barium ions, because that's how the sulfate test works that we and that we're going to get onto in a minute. So that suggests that it could be a barium 2 plus salt. So that's one possibility. It can't be an ammonium salt or a potassium salt, actually, because both of those ions, all their compounds, all their simple compounds are soluble, so they're not going to precipitate out. But even if you didn't know that, just keeping this in mind for the moment is going to give you the right answer in a minute. Right, second test with excuse me, barium nitrate solution, and there's no reaction. So that tells you it's not a sulfate. Because if it were a sulfate, you would get the white precipitate with barium nitrate. So that means it's not A either. So we've ruled out A and C, so that makes it between B and D, which are both barium compounds, so that fits with that one, so that seems to work. But we need to know, is it the chloride or is it the iodide? And that's where the third test comes in, which is the silver nitrate test, which gives us a precipitate, as we knew it would, because both chloride and iodide give precipitates. Had it told us the colour, we would be able to distinguish on the basis of that, because the chloride would be white, the iodide would be yellow, but it doesn't. It just gives us solubility in concentrated ammonia, so you have to remember the trend here. That silver chloride is soluble in ammonia even at low concentration. Silver bromide is soluble in ammonia but only at high concentration. Silver iodide is insoluble in ammonia at any concentration. So if the precipitate is insoluble in concentrated ammonia, it can only be the iodide, and therefore it must be an iodide ion. So we have the barium and the iodide, which means that BaI2, barium iodide, is the right answer, which was D. Question 14, you have to remember that these group 7 elements, their ability to gain an extra electron decreases as you go down the group. As you add more shells on and the outer shell becomes further from the nucleus and more shielded from it, the ability to attract an extra electron into it, and therefore to oxidize something else, decreases. So what that means is that in these competition reactions between two halogens, the one that's higher in the group will always succeed in getting the extra electron, and therefore will end up as the negative ion. Now in this case, we've got Cl- here, and we've got Br2 here. The chlorine is the element higher in the group, and it's already the negative ion, so nothing's going to happen. Okay, Br2 can't take the extra electron away from it, and so there will be no reaction in that case. So then you think, okay, in that case, what do we see when we add cyclohexane? Well, what we're going to see is the colour of the bromine, because it hasn't reacted with anything, and bromine, remember, is orange. It doesn't matter whether it's in water or in cyclohexane, it gives an orange solution. So orange was the answer, which was C. Question 15, we have to compare the conductivities of these substances in aqueous solution. So lithium fluoride is ionic, so that in aqueous solution we'll have mobile ions, so that will give you high conductivity. So that one's unlikely to be the answer. Methanol dissolves in water because it can form hydrogen bonds to the water using its OH group, but when it does that, it's still just a molecule. So there are no delocalized electrons, they're all contained within the molecule, and there are no ions. So that's just a molecular solution, and therefore we'd expect that to have a low conductivity, so that's a candidate. These two also dissolve, and on the face of it you think, well, they're molecules as well, but in both cases what you need to remember is that they react with the water. So when that one dissolves in water, you get this reaction. Chlorine plus water, remember, gives you reversibly HCl plus HOCl, and these are acids. Okay, so acids in aqueous solution give you H plus and the negative ion, so Cl minus or ClO minus ions will be present. So these solutions contain ions, and therefore they will be conductors. Maybe not as good as lithium fluoride, but certainly better than methanol. And we get a similar story with ammonia. Remember, ammonia dissolves in water to form an alkaline solution. This already came up in one of the earlier questions. Gives you NH4 plus and OH minus. Because ammonia is a base, it can use its lone pair on the nitrogen to take away H plus from the water to make NH4 plus, and that leaves OH minus behind. So again, we've got ions, and therefore this too will contain conductors. So neither of these will have very low conductivity, and therefore that's the one that does. So B is the answer. Question 16 is an MC delta T question, so it's going to be based on this relationship, which you know, and you should have realised that as soon as it mentioned specific heat capacity. Most of the questions you've ever done have been talking about the specific heat capacity of water, but this one isn't. It's about tin, but it doesn't make any difference. It's still the same relationship, and what we have to do is to solve for that. C is the one we're trying to find out. So M and delta T, we've got to move over to that side. So remember, things slide diagonally across. So we get Q divided by M delta T is equal to C. So just quickly do the rearrangement first, then plug the numbers in. So Q is the heat transferred. Now it gives us that number in kilojoules, so it's 1.0 kilojoules, but remember it needs to be in joules to make it compatible with the units of C, which are in joules per gram per Kelvin. So that's 1,000 joules is the same as 1 kilojoule. M is the mass of the tin, and it tells us we've got 1 mole of it, so the mass will be the AR, that number of grams. So you look up the AR and it's 118.7, so that means we have 118.7 grams of tin. And delta T is the temperature change, which is 40.0 degrees C. Remember, that's the same size of change in Kelvin, so that's 40.0 Kelvin. And so if you multiply those out, you get 0.21 is the numerical answer, and the units are joules per gram per Kelvin, which is what they needed to be. So that's the right answer, which was C. Question 17 is simply a matter of looking up those ranges on your data sheet. So 1630 to 1820 tells you have a carbonyl group, C double bond O, somewhere in your molecule, and the other one, 3200 to 3600, is an OH, but remember with OHs it's not just any old OH, it can distinguish between alcohols and carboxylic acids, so that is an alcohol OH. So we just have to look through and see which of those structures have both of those things. So pentan 2,3-diol is that. Diol means it has 2 alcohol OH groups, so it has that one but it doesn't have that one, so it can't be that. 5-hydroxy-pentan 2-one. Pentan 2-one means you have a ketone group at carbon 2, and 5-hydroxy is there, so that one fits the bill because it's got the carbonyl group, hasn't got the OH group. So we could just tick that one and move on, but if we just check out the other two, pentanoic acid is that. So it has the carbonyl group, it has an OH, but it's the wrong kind. It's not an alcohol OH, so it can't be that one. Now the last one is the one where you have to be quite careful, 3-hydroxy pentanoic acid. Is this. So there's this is carbon 1, which is carboxylic acid carbon, so that's the 3-hydroxy group. Now you might think, well, that has a carbonyl group and it has an alcohol OH, so why can't it be that one? But the point is it has a carboxylic acid OH as well. And if you remember what the spectra look like, if you have an alcohol, it sort of looks like that. So if those are the CHs around 3000 wave numbers, an alcohol OH looks like that. A carboxylic acid OH overlaps with it. So a carboxylic acid OH, if we drew that one in, would look kind of like that. And so the point is they overlap, so you wouldn't see a clear peak like that, it would be merged with the carboxylic acid one, and so you'd get a huge broad peak sort of like that spanning that whole range rather than just 3,200 to 3,600. So that one is ruled out as well. Okay, so question 18, we have to use the Kern-Ingold-Prelog rules to assign EZ configurations to each of these alkene groups. So if we focus on this one first of all, the left-hand one, at this end of the double bond you've got carbon with atomic number 6, fluorine with atomic number 9. So fluorine trumps carbon, so that's the priority group at the left-hand end. At the other end you've got carbon here and hydrogen here, so atomic number 6 and 1, so this one is the dominant one, the priority one on that side. So the two priority groups are on the same side of the double bond, and therefore that one is a Z configuration. Now if we focus on the other one, second double bond, which is this one, so at this end you've got carbon and hydrogen at this end of the double bond, so this one has the priority because it's got the higher atomic number. At this end you've got chlorine and fluorine, so atomic number 17 and 9, so 17 wins. And so again, the two high priority groups are on the same side of the double bond, so that one is Z as well, and if they're both Z, the answer is D. Question 19 then is asking us which of these substances will give the highest pH in a saturated solution. Make sure you know what that word saturated means. It just means when you've dissolved as much of it as you can possibly dissolve. So which would then give the solution with the highest concentration of OH minus ions and therefore the highest pH. So clearly not that one. That's an acid, not an alkali, so that's not going to have many OH minus ions at all, so we can straight away rule that one out. The other three are all bases, but ammonia, you have to remember, is a weak base, okay, because it only reacts reversibly with water. We keep coming back to this reaction. It's very important to know this about ammonia, that yes, it does have OH minus ions in solution as a result of that reaction, but because it's reversible, you only get a relatively modest amount of them. So that's not likely to have the highest pH, because these two substances are strong bases. They actually contain OH minus ions, so when you dissolve them, all of the OH minus ions are liberated. So what it comes down to is comparing these two and thinking about the solubility. And so we know the trend in solubility as you go down, group 2, is that the hydroxides become more soluble. So this is the more soluble strong base. Magnesium hydroxide is also a strong base, but it's just not very soluble, so there's not going to be a very high concentration of OH minus for that one, but there is for this one, and therefore that's going to be the winner. So A was the right answer for that one. Question 20 is a case really of just remembering the definition of an electrophile, which is that an electrophile is a okay, let's try that one again. Question 20 is a case really just of remembering what the definition is for an electrophile, which is that it's an electron pair acceptor. So what that means is that an electrophile has to be capable of attracting a pair of electrons away from the molecule that it's attacking. And of course the best way to attract a pair of electrons is to be positively charged. And so just looking at that list, it's got to be that one, because that one's going to be rubbish. If you're trying to attract a pair of electrons, the last thing you want to be in is negatively charged. These ones, well, maybe, but there's no particular reason to think they're able to attract electrons, but this one with its positive charge should be able to do a good job, so C was the answer for that one.